Hi everyone, this is Mrs. GA, and today we're going to be talking about the derivative as a function. All right, I have a quick warm up for you guys, so pause the video and hit play when you're ready to check. All right, go ahead and check your work here. So you can see that first I use this formula, and then to help us evaluate the limit, I combined the two fractions in the numerator, and then I just started simplifying. What I was left with was the limit as x approaches a of 3 over 3 plus x times 3 plus a, which you can evaluate this limit just using direct substitution. So our slope of this function at any point at x equals a would be 3 over 3 plus a squared. So you could evaluate the slope of your line at any value just by substituting that value for a. So last class, when we were talking about the derivative, we learned the derivative of a function at some value x equals a. And we did that one way with this formula. So f prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h. And again, the distance between these two x values is just h. So this was one definition, but again, we're evaluating the derivative at some value a. So this class, we're going to define the derivative as its own new function, so f prime of x. So essentially all we're doing is replacing the variable a with the variable x now. So it's the same thing. We're still defining two points as x and x plus h. So again, that distance between the two here is h. And essentially we're finding the limit as h approaches 0 of the slope between those 2 points. So again, we're just thinking of the derivative now as its own new function, which we'll call f prime of x. So some notation and vocabulary that's going to be really important as we continue to work with derivatives. So f prime of x, that's a really common way to write the first derivative, or we could say y prime. We could also use that Leibniz notation, so dy dx, or df dx, or d dx of f of x, depending on which notation you want to use, or you can even use these notations here. Not as common, but you still might see them. Now, if you want to use this Leibniz notation, this one right here, but you want to specify the value that you're taking the derivative at. So if you want to specify that a value, you can simply do a vertical line or this bracket to the right, and then just define what your value is down at the bottom right. So you'll see, like, if you use this notation, f prime of x, you can plug in whatever value, or you could you can indicate the value here. But if you're using this notation, you can't indicate the value that you're differentiating at. Which brings us to a couple pieces of vocabulary that we'll be using a lot. Differentiate is just a verb. It's just to take the derivative of. And notice in all of these examples, we're taking the derivative of y with respect to x. So this is all differentiating. And the adjective differentiable just describes a function that you can differentiate. So if the function is differentiable, it just means that you can differentiate it at that value. All right, so next let's look at a couple definitions we'll be working with today. First, a function f is differentiable at a if f prime of a exists. So if the derivative exists at x equals a, it's differentiable at a. So this next part's pretty intuitive. It is differentiable on an open interval a to b, or different intervals listed here, if it is differentiable at every number in the interval. So if we say a function is differentiable over an interval, it means that everything in between is differentiable. All right, now let's look at this next definition. So this says if f is differentiable at a, then f is continuous at a. So if it is differentiable, then it's continuous at a. But I do want to note that the converse of this statement is not necessarily true. So while we can say that if we know something is differentiable, we can say it must be continuous, just because something is continuous does not make it necessarily differentiable. So again, a function can be continuous, but not differentiable. But again, just to nail this point home, if it is differentiable at a, it is continuous at a. All right, let's continue to look at this relationship between differentiability and continuity. So let's consider this function, f of x equals the absolute value of x minus 4. We're going to look at where this function is continuous and where it is differentiable. So just a quick sketch of our function, just so we can kind of visualize what we're working with. It's this V-shaped graph, and this vertex here is at 4, 0, because our graph has just been shifted to the right 4. So absolute value functions are continuous over the interval all real numbers. So we know that we can draw this function without picking up our pencil. There's no discontinuities in this function. But now what I want to talk about is, well, just because our graph is continuous on all real numbers, does that necessarily mean that it's differentiable over all real numbers? So there's a really specific point I want to look at and focus on, and that's the vertex right here. So I want to know if it's differentiable at the vertex. So remember, since we do have a absolute value function, we do have to kind of consider this as a piecewise function on the left and the right. So everything to the right of our vertex will just be x minus 4. So that's for when x is greater than 4. But everything to the left of our vertex, it's the opposite of what's inside your absolute value. So it's negative x plus 4 for everything to the left. And I purposely left out the vertex. I know with our piecewise, sometimes we include it in the top or the bottom. But when we're evaluating the derivative, I'm going to kind of keep it separate, because really what we're going to do is we're going to find the limit as x approaches 4. So we're going to do f of x minus f of 4 over x minus 4. And again, since we do have this kind of piecewise function, we need to evaluate the left and the right handed limits. So let's find the limit as x approaches 4 from the left. So for this, we're going to use this portion of our function. So f of x is negative x plus 4. And then we're going to subtract f of 4, which if you use this portion of our function, it's actually 0. And over x minus 4. And let's evaluate this limit. So here you can actually see that we can factor out the negative here, and we're left with negative and then x minus 4 over x minus 4. So really we're just finding the limit as x approaches 4 from the left of negative 1, which is of course just negative 1. So that's our left-handed limit. So now let's find our right-handed limit. So the limit as x approaches 4 from the right. So this time I'm going to use this portion of our function. So here we have x minus 4, that's f of x, and f of 4 is still 0, and then over x minus 4. So from here you can see that we have the limit as x approaches 4 from the right of just 1, which equals 1. So you'll see here that our left-handed and our right-handed limits are not the same. And so since they're not the same, this limit does not exist. So we could say does not exist. And since the limit doesn't exist for this, we would say that our graph is not differentiable at that point at x equals 4. Now, you would find that if you just tried to differentiate just this portion of your graph, so everything to the right of 4, you'd find that it is differentiable. And if you just tried to differentiate this portion of our graph, so everything to the left of our vertex, it is also differentiable. But it is not differentiable at the vertex when x equals 4. And again, that's because the left and the right-handed limits are not the same. So that limit does not exist. So here, this is a clear example of when a graph can be continuous at a value, but not differentiable at that value. So I want to kind of do an overview of the different ways a function can fail to be differentiable at a specific value. So the first case is just like the last example we looked at. When you have values that make your function do a really sharp turn, like in an absolute value function at the vertex, or if you come to kind of like a corner or a cusp, your graph is not going to be differentiable at that value. So if you look at that graph in example A right here, at this point, our graph would not be differentiable. It could be differentiable for the rest of the function, but it would not be differentiable when it makes that sharp turn. Another scenario where your graph would fail to be differentiable is when the graph is not continuous, and that does have to do with that definition that we talked about earlier. So if a graph is differentiable, then it is continuous. So therefore, if it's not continuous, it's definitely not differentiable. So if you have something like this, it will not be differentiable when x is equal to a. And the third case when a graph might fail to be differentiable is when is at values where the graph has a vertical tangent line. So if you kind of look at a graph that looks something like this, you can see in this picture when x is equal to a, you have a vertical tangent line. So again, your graph would not be differentiable when x is equal to a. So those are kind of the three cases that we look for to determine if a graph or a function is differentiable at a specific value. All right, so now we're going to try sketching graphs of our derivative function, f prime. So we know that the derivative of our function, f prime, represents the slope of the tangent line at any given point. So we know that if we look at what the slope of f of x is, we can use that to help us start sketching f prime of x. So when I'm doing this, the first thing I'm going to look for is when our graph changes from decreasing to increasing or vice versa, because that's when the slope is changing from negative to positive or positive to negative. So it might help for you to color code your graph. So I could see that our graph is decreasing in this interval and this interval, and our graph is increasing in this interval and this interval. So I know that where f of x is red, f prime of x is going to be negative, so it'll be below the x-axis. And I know where f of x is green, f prime of x is going to be positive, because again, the slope is positive, so it'll be above the x-axis. So I'm really going to start by looking for those turning points, which are right here, here, and here. Because this is actually when my slope is 0. So here it's changing from negative to positive. So somewhere in between, the slope must be 0, and it's going to happen right at those turning points. So I know that these are going to become the x-intercepts of my derivative of f prime. So we're going to do a really rough sketch here. So I see that this turning point occurs somewhere between -1 and -2, so I'll just kind of estimate. So it'll be about here. And then I can see that I have another turning point at 2. It's just a coincidence that it's also an x-intercept. That doesn't really matter. What matters is the slope is changing from positive or from increasing to decreasing. So that happens at 2. And then I see that my slope changes again from negative to positive at +4. So again, everything up until this point, our graph, the slope is negative, so f prime is going to be below the x-axis. So it'll look like this. And then I see that after that, our graph is increasing, so the slope is positive, so it'll be above the x-axis until it hits 2, when our slope is negative, so our derivative will be below the x-axis, until we hit 4, and then everything to the right of 4, the slope is positive, so our derivative, f prime, will be above the x-axis. So notice again where f of x is red, my graph is below the x-axis. So that was this region and this region. And where f of x is green, so where the slope is positive, f prime is above the x-axis. So that would be this region and this region. So remember, to graph the derivative, we are looking at what the slope of our original function is. So just look for those turning points and then just ask yourself, is my slope positive or is my slope negative? Is my graph decreasing or is my graph increasing? All right, so I have one for you to try, so please pause the video and hit play when you're ready to check. All right, go ahead and check your work here. So this one is a little bit tricky because at this value 2, you can see that our graph actually does slow down and it almost becomes, it looks like it's going to turn around, but then it actually continues increasing again. So in this entire interval, our slope is positive. However, it does flatten out. So the slope does become 0 again just for a second, but again, notice in this entire interval, it is always, g prime is always above the x-axis because our slope is always positive. And notice between -1 and 0, g prime is negative because that's where our slope is negative. And everything to the right of maybe about 3.5, or I just kind of estimated where that was, g prime is below the x-axis again because our slope is negative. All right, so we're going to try another one together. We're going to try to sketch a graph of a function f that is continuous for all values and has the following characteristics. So first it says that f of 0 is 0. So we know we could just plot that point. It tells us that f of 1 is 2, f of 2 is 1, and f of 3 is 0. And then we're told a couple of extra things about the derivative. So we are told that f prime of 0 is 0, f prime of 1 is 0, and f prime of 2 is 0. So whenever we are told that the derivative at a value is equal to 0, we know that that means that our graph is flattening out. So we know that our graph is kind of maybe hitting a min or a max at those values. So we know that that's happening right here at x equals 0 and at x equals 1 and at x equals 2. So essentially our graph is going to be changing from positive to negative, or again flattening out at those values. So to make all of our points connect and to still meet these last three characteristics, I know that our graph is going to do something like this. So you can see that we're changing from negative to positive, so it will eventually be 0 at some point, and then it will do something like this. And then from here, we could do a couple different things. We could have it kind of turn around like this, but I know it does need to turn around again to go through that last point at f of 3 is equal to 0. Or alternatively, maybe instead of completely turning around like we kind of saw in that last example, our graph, we could just have it kind of flatten out. So I'll kind of show in green. It could flatten out and then just kind of continue onward like this. So either way, at this point, the slope of our function is equal to 0. So either way would technically fit the characteristics given in the example. Okay, so now we're going to actually practice finding our derivative function. So we're going to find the derivative of f of x using that formal definition using a limit. So here's our first function, f of x equals the square root of 3x plus 1. So we're going to find the limit as h approaches 0, first of f of x plus h. So that would be the square root of 3 times x plus h plus 1 minus f of x. So square root of 3x plus 1 all over h. And now we just need to evaluate the limit. So here it may be helpful to multiply by the conjugate. So the square root of 3x plus 3h plus 1 plus the square root of 3x plus 1, and I'll multiply by that in the denominator as well. So here we have the limit as h approaches 0 of 3x plus 3h plus 1 minus 3x plus 1, be careful with those parentheses, all over h times our conjugate. All right, let's try to simplify what's going on in the numerator. So here you could see that our x's will cancel out and the 1's will cancel out, and we're left with 3h over h. So we just have 3 over the square root of 3x plus 3h plus 1 plus the square root of 3x plus 1. So this limit we can evaluate using direct substitution. So I'll just substitute h with 0. So again, this just essentially becomes 0. So our limit is equal to 3 over, here we have the same radical added twice. So 3 over 2 times the square root of 3x plus 1. So this would be our derivative. And there you go. So just remember these, they look like they're going to be really, really convoluted at first, but you'll see in just a couple steps that they actually cancel out pretty nicely. So don't be intimidated when you see a problem like this. All right, let's try another one together. So here we have the function f of x equals x squared plus 1 over x minus 2. So we'll use that same limit definition. So first, f of x plus h. So we have x plus h squared plus 1 over x plus h minus 2. And then we have minus f of x all over h. So here we are going to want to combine the fractions in the numerator by making a common denominator, essentially. So we have the limit as h approaches 0. So this one I'm going to multiply by x minus 2 over x minus 2. And this one I will multiply by x plus h minus 2 over x plus h minus 2. And I'll make sure to group these as well. So that leaves us with x minus 2. And then this we can multiply out. So x squared plus 2xh plus h squared plus 1 minus x squared plus 1 times x plus h minus 2 all over h times x minus 2 times x plus h minus 2. So everything in my denominator all got multiplied and lumped into a single denominator. So from here, we really just need to start multiplying it out. So this step is a little bit tedious, but we just got to work through it. So here we have x cubed plus 2x squared h plus xh squared plus x minus 2x squared minus 4xh minus 2h squared minus 2. And then we also need to multiply this out. So again, just stick with it for a couple steps. So here I'm going to subtract and then I'm going to group whatever is the product. So x cubed plus x squared h minus 2x squared plus x plus h minus 2. And then all of this is over h times x minus 2 times x plus h minus 2. All right, now let's see what we can cancel out. So we have x cubed and then we have minus x cubed here. We have positive x and this does become negative x when you distribute. And let's see, we have negative 2x squared and then this does become positive 2x squared. And last we have negative 2 and positive 2 that we can just cancel out. And then let's see what we have left. So the limit as h approaches 0. We can combine the 2xh and then the minus x squared h. So that just leaves us with 1x squared h. So x squared h and then plus xh squared minus 4xh minus 2h squared. And then we do have that minus h left over here. All over h times x minus 2 times x plus h minus 2. You might notice that all of our terms in the numerator do have an h, so we can divide out h. So that leaves us with x squared plus xh minus 4x minus 2h minus 1 over x minus 2 times x plus h minus 2. And now we can evaluate this limit using direct substitution. So anywhere where we see an h, I'll replace it with a 0. So this will become 0, this will become 0, and this will become 0. So that leaves us with x squared minus 4x minus 1 over x minus 2 times x minus 2. So our derivative, f prime of x, is x squared minus 4x minus 1 over x minus 2 squared. So this one definitely is a little bit more tedious. But again, if you look at all the steps, it is, it's stuff that you can do. It's just multiplying out polynomials. You do just need to be careful, especially with your negatives. So for these, it's really important that you show out every step. I'd say don't try to do these in your head. Write everything out. All right, I have one for you to try on your own. So go ahead and pause the video and give it a shot. All right, go ahead and check your work here. Just be careful that you remember to distribute that negative. So our derivative is negative 1 over 3 plus x squared. All right, so now we're going to kind of try to work our way backwards. So here we're going to look at a derivative that's in limit form and see if we can find the function and the value that the limit or that the derivative represents. So if you look at this first one, you can see that it's kind of in this form of h approaches 0 of f of a plus h minus f of a over h. So for this one, you could see that here we substituted the a plus h into some function. So we know that that function must have been the fourth root of x. And that you can see that what we plugged into this function would have been the a value of 16. And that does check out because if we do f of a, so f of 16, the fourth root of 16 is 2. So this would be the original function, and then this would be the a value. And again, we're kind of just working our way backwards from that limit form. Now, if you look at this second example here, this is in that form, the limit as x approaches a of f of x minus f of a over x minus a. So from this form, you can see that our a value right here is pi over 4. And you could see that our function is just tangent of x. And that does check out because the tangent of pi over 4 is equal to 1. So that would be f of pi over 4. So again, just looking at kind of two different representations of a derivative in limit form and working our way backwards to find the original function and the value that we're representing the derivative of. All right, I have one for you to try on your own, so pause the video and hit play when you're ready to check. All right, go ahead and check your work here. So you can see here, this represents the function, and you can see what we plugged into it, where it says a plus h is e squared plus h. So we know that the function must be natural log of x, and that a value must be e squared. And for this, well, if you do f of e squared, it does simplify to 2. The natural log of e squared is just 2. All right, the last concept we're going to talk about today is what are called higher order derivatives. So we know that the derivative of f of x is some new function, f prime of x. Now, you can actually take the derivative of f prime, and that becomes a new function in itself. So f double prime of x, which is called the second derivative. If you're using that Leibniz notation, we would say d dx of dy dx. So the derivative of the first derivative becomes the second derivative. So we write it as d squared y over dx squared. So the notation is a little bit funky, so you just need to be careful that you are writing it correctly. So this is just that notation for our second derivative. And you can also take the derivative of f double prime, and it becomes, again, its own new function, which would be the third derivative. So again, we can use a couple different notations here. We can do like the 3 tick marks, or we can use the Leibniz notation, and we can actually write it like this. So it'd be like d cubed of y over dx cubed. So to generalize that, any derivative past that, the nth derivative of y can be denoted by it looks like y to the power of n, or f to the power of n of x. So we would just actually write the number there. So if it's the fourth derivative, we'd actually just be writing the number 4 here, and then we can use that same kind of pattern and put that nth derivative here and here. So you can go as high as you want, but we will typically be working with maybe a second or a third derivative in our class. All right, so let's try another one together. Here we're given the function f of x is x cubed minus x, and we're told that the first derivative is 3x squared minus 1. So we're given f prime here. We want to find the second and the third derivatives. So first, to find the second derivative, we're going to take the derivative of f prime of x. So we're doing the derivative of 3x squared minus 1. Again, we can use our limit process here. So we're going to do 3 times x plus h squared minus 1 minus 3x squared minus 1 over h. Then this we just need to simplify out a little bit. So 3 times x squared plus 2xh plus h squared minus 1 minus 3x squared plus 1 all over h. So 3x squared plus 6xh plus 3h squared. And then you'll see we have the minus 1 plus 1. And we also have that 3x squared minus 3x squared. We can divide out the h. So that leaves us with 6x plus 3h. And then we can just evaluate this limit using direct substitution. So it just becomes 6x. So f double prime is 6x. But now we're going to find the third derivative. So the third derivative is just going to be the derivative of our second derivative, f double prime of x. So we're essentially finding the derivative of the function 6x. So we could use our limit. So limit as h approaches 0 of f of x plus h. So 6 times x plus h minus f of x, which is just 6x all over h. So if we simplify this, this gives us 6x plus 6h minus 6x. So we have 6h over h. So it's the limit as h approaches 0 of 6, which is 6. So our third derivative is just 6. So now I want to talk about some applications of derivatives. So when would we care about the first or second or third derivative? So suppose we go back to that position function that we've talked about in previous lessons. And this time we're going to represent that with s of t. So that could be represented by maybe like the height of an object over the number of seconds that has gone by. So the first derivative of a position function we already know is the velocity function, which we can call v of t. So you can see that s prime of t is v of t. So the first derivative of our position function is our velocity function. Now, the derivative of a velocity function, so if we take the derivative of the first derivative, we actually end up with the acceleration function, which we can represent with a of t. So notice that a of t is v prime of t. It's, again, the derivative of our velocity function, which is actually the second derivative of our position function. And then the derivative of the acceleration function is what we call a jerk function. And we can represent that with j of t. So again, that's the derivative of your acceleration function, or the first derivative of your acceleration function, which would be the second derivative of your velocity function, which is actually the third derivative of that position function. So hopefully this kind of makes sense. Again, if your position function, just consider maybe the height of an object over time in seconds. If you think about the change in position, That's simply velocity. Velocity is just how quickly you are changing position. And then if you think about, well, how quickly are you changing your velocity? That's the acceleration. And then if you think about how quickly are you accelerating, that would be considered jerk. So think about, when you're driving a car, if you accelerate really quickly, you actually like kind of jerk back. So maybe that's how you could kind of remember or visualize what this jerk function would represent. But all of these are simply just how quickly is the previous function changing. Velocity is change of position, acceleration is change in velocity, and jerk is change of acceleration. All right, let's try this last example together. So it says the height of a particle in feet over time in seconds is represented by this function, h of x equals x cubed minus x. And we want to know what is the acceleration of the particle at 8 seconds. So this is actually the same function that we worked with in example 6. So we've already found those derivatives. We just have to figure out what they're asking us to use. So we know that acceleration is the second derivative of our position function. So we were given that first derivative, which in this case would be the velocity, v of x, the velocity of our particle, and we were told that it was 3x squared minus 1. And then we found the second derivative, which in this case would be the acceleration function, and we found that it was 6x. So this function can tell us the acceleration of our particle at any moment in time. But here we wanted to know what's the acceleration of the particle after 8 seconds has gone by. So we simply substitute 8 into our second derivative or our acceleration function, and we find that it is 48. And then we need to be careful with our units. So this one is actually feet per second squared. So remember, the velocity would just be feet per second, and then each time we're finding the rate of change of that would add that extra unit in our denominator. So it's 48 feet per second squared. So hopefully now you can see how we might be able to use our first or second or even third derivative of our position function. All right, so that is all for today's video. Thank you guys for watching.